Welcome to lecture number 7. Today we would continue the kinetics of enzyme inhibition. So in last lecture, that is in lecture number 6, we discussed that there are three types. There are two basic types of enzyme inhibition. One is called the reversible inhibition and another is irreversible inhibition. And we learned that in irreversible inhibition, the inhibitors actually destroy the enzymes and no product is formed. But in reversible inhibition, the inhibitors don't destroy the enzymes, product is formed, but with some difficulty and with some complexities. So depending on the mechanism of these inhibitions, or better the mechanism of reversible inhibitions, that is divided into three categories. So one is called the competitive inhibition that we have already covered in lecture number 6. So today we are going to learn about the two other types, that is uncompetitive inhibitor and the mixed inhibitor or inhibition. So today we first start with this, the uncompetitive inhibition. So in this inhibition, what happens is, first let's write the enzyme kinetics in stepwise, then we will write some cartoon diagrams. So the enzyme under normal circumstances binds with the substrate to form the enzyme substrate complex, and that breaks down to the product plus enzyme, and that we have already familiar with. But in uncompetitive inhibition, what happens that this enzyme substrate complex actually interacts with the inhibitor. So here, unlike the competitive inhibition, the inhibitor directly attacks the enzyme substrate complex rather than attacking the enzyme. So therefore, what we have here is basically an enzyme substrate inhibitor complex, and the forward rate constant is known as K1 double prime, and the backward can be denoted as K2 double prime. And so we can actually write plus I here because ES needs to react with this inhibitor. And once ESI is formed, it fails to give any product. So that is the no product. And this type of inhibition is called the uncompetitive inhibition. And we can represent the same by a cartoon diagram. So this is the enzyme E, and this is the substrate S, is something like this, and the substrate actually binds to the substrate binding site. So actually I'm going to make one more correction over here. So this is the substrate, and so the enzyme would bind to the substrate binding site. So this is the substrate binding site and this is the active site. So this forms the ES complex. But you see, there is another position available for the inhibitor. So here the inhibitor may be thought of having a different geometry which is unable to directly bind to this active site, but it can bind to the enzyme substrate complex to any other site so that it can block the enzyme's activity. So what it does is basically, so this is the enzyme substrate complex, so the inhibitor actually binds to another site over here. So this is called the enzyme substrate inhibitor complex, and it fails to give you any product. So what did we learn? And we learned that the major difference with the competitive and uncompetitive inhibitor is the inhibitor does not compete with the substrate because it does not have the similar geometry to fit in the active site. But we call the other inhibitor that we have learned in lecture number 6, we call that competitive inhibitor because that inhibitor actually competes with the substrate because having similarity in the geometry. Okay, so like we have done before, we have to derive the rate equation for the uncompetitive inhibition. So the strategy for the competitive inhibitor I have clearly laid out on the board. So this time we have to follow the same approach. That means the approximation of steady state. But it's your job now to try that, because let me assume that you have understood, or better, if you have understood how the steady state approximation was applied in the earlier case, you would be able to do it similarly here. Okay, so remember, I can give you a couple of hints that here we have two species now, ES and ESI. So we have to apply the steady state approximation for both the two intermediates. Remember, ESI is also an intermediate and ES is also an intermediate. So we have to apply these conditions, that is DES dt is equal to 0, and also we have to apply the DESI dt is equal to 0. So from these two conditions, finally we have to find it out that V is equal to, of course, velocity is K3 multiplied by ES. Okay, and if you remember earlier that ES actually it has some expression. Okay, so it can be related with Km and with the substrate concentration. So from that we have to write an expression over here, and that expression would contain some terms. So those terms should be found out from these two equations, and there will be one more equations where we relate the total enzyme concentration with something, that means the unreacted enzyme plus something, etc. Okay, so these are the hints, and if you have followed the case for the competitive inhibition, I am quite sure you will be able to get this. Okay, so let's look forward that what happens finally. Okay, so let me clean the board and write down the expected results, and let's take it from there. So if we solve the kinetics of the uncompetitive inhibition by applying the approximation of steady state, we should be getting an equation something like that: Vmax multiplied by S divided by Michaelis constant plus alpha prime multiplied by the substrate concentration, where alpha prime is very similar to alpha, but it is 1 plus K1 double prime divided by K2 double prime multiplied by inhibitor concentration. So therefore, we can write the above equation in terms of the Lineweaver-Burke form. So if we convert that into Lineweaver-Burke form, we will get 1 over V is equal to alpha prime divided by Vmax plus Km divided by Vmax multiplied by 1 over S. So once again, you see this is an equation for the straight line, y is equal to C plus Mx. So here what we see that this is the intercept, okay, and this is the slope. So with increasing I, so we can write that with increasing concentration of the inhibitors. So suppose if I write like alpha, so we have alpha prime, so alpha 1 prime less than alpha 2 prime less than alpha 3 prime, etc. With increasing concentration of I, we see the slope is unchanged, so the slope remains constant. But the intercept on the vertical axis increases with increasing concentration of I. Okay, so now this gives an interesting case. So we have to draw the graph plot of such Lineweaver-Burke equation of uncompetitive inhibitor with increasing concentration giving us the constant slopes but an increasing intercept on the vertical axis. Okay, so let's quickly clean the board and let's draw the graph plot. So here we go. We have 1 over S in the horizontal axis and 1 over V in the vertical axis. So let's first draw the graph plot for uninhibited situation. So this is the uninhibited straight line, and here the inhibitor concentration is 0, that means it is not inhibited. So once we have some inhibitor concentration, we have constant slope but increasing vertical intercept. So let's assume that the new intercept is this. Okay, so therefore if we want to keep the slopes same, we have to draw a straight line parallel to I is equal to 0. So we can say here that here alpha prime is equal to 1, but here we have alpha prime 1, which is greater than alpha prime. And once again, with increasing I, we can draw more graph plots. So let's assume that the new intercept is this one, and therefore once again we have to draw a parallel line like this, and this time this is alpha 2 prime, which is greater than alpha 1 prime. So this curve has been drawn with increasing concentration of I. Alright. Now interestingly, you see that here in the horizontal axis it has some intercepts, and these intercepts are also changing. So what does those intercepts mean? Okay, so if you have followed it correctly, then probably you can recognize that this represents apparent Michaelis constant, and with changing I, can you assess or calculate how does the apparent Michaelis constant behave in this case, whether it increases or decreases, and if so, what are the physical interpretation can you make out? Okay, so this summarizes the uncompetitive inhibition, but before we move on to the mixed inhibition, the questions for you that there are 3 parameters, as I told you last time when we discussed the competitive inhibitor, that velocity and Vmax and Km. So these are 3 very important parameters for enzyme inhibition. For this uncompetitive inhibition, it's your job to summarize all these 3. So what happens to the velocity increases or decreases, what happens to the apparent maximum velocity increases or decreases, and what happens to the apparent Km, whether it increases, decreases, or stay same. Okay, and likewise, can you draw the Michaelis-Menten graph plot, that is V versus S plot? Okay, So we will try those we will revisit those problems once again in the form of some tutorial assignments. Okay. So now let's move on to the last type of major enzyme inhibition, which is mixed inhibition. So let's work it out. So when you talk about the mixed inhibition, as you see on the board, we have written a reaction scheme that contains both the competitive and uncompetitive inhibition together. So if you look at here, enzyme plus substrate when uninhibited gives ES and the product, but the enzyme in presence of some inhibitor, it gives EI. And remember, the inhibitor is equally capable to bind on the active site to make EI in a competitive manner, and also it can bind to the enzyme substrate complex to other non-active sites to give ESI, the enzyme substrate inhibitor complex. So therefore the mixed inhibition is defined as simultaneous action of competitive and uncompetitive inhibition. So this part you can recognize is a competitive inhibition scheme, and this part is uncompetitive inhibition scheme. So everything else is, I believe, that is already familiar to you, and I'm not going to draw the cartoon diagram once again because I have already drawn those diagrams, and those are identical with these individual steps. But two things to remember, that whenever EI is formed there is no product, and whenever ESI is formed there is no product. Although I have written that these two things, EI plus S and ESI, may be reversible, but they don't have any effect on the product formation. So basically we have to concentrate on this pathway, this whole pathway, and also individually to this pathway. Okay, so basically we have three routes. Route number 1 going into this direction, and route number 2 going into this direction, and route number 3 going into this direction. So therefore in the same manner we have to apply the steady state approximation. So you can fearlessly apply the approximation of steady state, and then you follow exactly the same path or same manner of solving this that you have followed already in competitive and uncompetitive inhibition. So that means you have to identify the intermediates. Of course there are three intermediates, these and these, and therefore obviously you can apply these approximations, and by now this kind of treatment should be very familiar to us. So if I apply this approximation, and also there is one more equation, that total enzyme E naught is the unreacted enzyme plus some more concentration terms where the enzyme E can be found. So therefore we have these three conditions and this equation. By taking help all those four equations, you have to arrive at the correct expression for the inhibition kinetics for mixed inhibition. Okay, so let's clean the board and let's see that what you are going to figure out finally if you do all those steps correctly. So let's check it out. So the expression should come out to be Vmax multiplied by S divided by, now you see here all the two types of alpha would appear, alpha Km and alpha prime S, and where it's needless to say that the expressions for alpha and alpha prime is the same. So alpha for this one was the competitive inhibitor and this one is for the uncompetitive inhibitor. Now if we try to express the same thing into the Lineweaver-Burke form, so it will take up something like this: 1 over V is equal to alpha prime divided by Vmax plus alpha Km divided by Vmax multiplied by 1 over S. Now you see, once again, this is an equation for a straight line, but here the intercept would also change with the concentration of I. That means with increasing I concentration, the intercept on the vertical axis will increase, and also the slope. Now the slope part contains alpha, so that means like competitive inhibitor, with increasing inhibitor concentration, the slope will also increase. So basically, since all the possible things are going on, like both the competitive and uncompetitive, the graph plot would exactly reflect the same. That means the graph plot would be a combination of the both competitive and uncompetitive inhibition. So can we try to draw the Lineweaver-Burke form of this mixed inhibition? So it would be easy this time, and in fact we will try to draw it with increasing concentration of I. So let's do that. So like before, we would first draw the uninhibited plot. So here this is I is equal to 0. So now we are going to draw the straight line for increasing I. Now before we going to draw, we would first ask ourselves two important questions. Is the Vmax means intercept changing on the vertical axis? Yes, it's increasing. The slope increasing? Yes. What about the apparent Km? Because the apparent Km would tell you from where this graph will start when 1 over S value is 0. Okay? So from the graph plot, probably you can guess that the apparent Km should also be changing. So therefore, for increasing I, let's take an arbitrary case where this is an increased intercept, and therefore we are thinking about an increased slope. So let's draw something like that. Okay, so this straight line represents an increased slope, so we can actually extrapolate here with, so this intercept will also change, and again with further increase of I, so we can choose this vertical intercept, and we can even choose a steeper slope, so we can draw a straight line, something like that. Okay, so as you see, so these straight lines have been arranged with an increasing I. So here you see everything changes, the slope changes, the intercept on the vertical axis changes, and also the intercept on the horizontal axis also changes. So in a nutshell, this is the summary of mixed inhibition, but you have to make sure how the inhibition is working. So that means whether how the velocity is changing, how the intercept, that means Vmax is changing, and how the apparent Km is changing for mixed inhibition. You have to have a summarized picture in your mind, and it doesn't end here everything, because we still did not draw the V versus S curve for this kind of mixed inhibition. Okay, so it's your job to do it, so you can spend some time on it thinking, and then you can try to draw those graph plots yourself, and I will come back in the tutorial session to verify that whether you have drawn it correctly, and if you are able to draw all those graph plots correctly with correct parameters, then your understanding on enzyme kinetics and kinetics of enzyme inhibition would be regarded complete. Okay, so that's how we finish the homogeneous catalysis, and we will come back with some tutorial problems, and I will try to help you to solve those problems, because I believe during the tutorials we will get a little bit more knowledge. And so for this course we are left with lecture 8, where we will deal with heterogeneous catalysis. So I hope you are enjoying these video lectures. So please go through your study materials and the lecture itself, and please spend some time to understand the materials, and stay put, and I will see you in the next lecture. Till then, goodbye.